Hi, I'm Chase, and today I'm going to show you how to solve this mysterious differential equation. Okay, so it turns out that this is a first order linear differential equation. And we have as far as differential equations go, relatively simple trick to solve it. So what we're going to do is first we're going to put it into the standard form for a first order linear differential equation. And what that requires is that we're going to divide everything by cos x. And don't worry, I know cos x is sometimes 0, but and that might create singular points. But we will worry about that later. So now that we have our first order linear differential equation in standard form, the next step that we have to do is well, let's just write out the general form of standard form. Y prime plus p of x y equal p of x times y equals f of x. This is standard form for a first order linear differential equation. What we need to do next is find the integrating factor. So the integrating factor mu, I got my Unicode character input here. The formula for it is just to find mu equals e to the integral of p with respect to x. And there's a reason for this, and just because then mu prime equals p times u, and and because we use the product rule, and there's a whole bunch of reasons for why this is but I'm just going to skip over that and just get to the computation. Assume you're familiar already with solving first order linear differential equations, in which case this one wouldn't be so hard for you anyways. But the next step is to rewrite the equation like so: 3b. So now the next step is, if we integrate both sides of this equation we have here, we get y times mu on the left side, and on the right hand side we get the integral of mu times p. Remember, these are both functions of x with respect to x. So we are just going to focus on this integral for now and worry about the rest of the equation later. Mu, as we defined earlier, is e to the integral of p dx. And so that is going to be e to the, and I've already solved this. But the integral of tangent of x is equal to ln of absolute value of cos x plus c plus a constant. And this can be simplified a lot. Sorry, negative ln of cos x plus c. And this can be simplified greatly to some constant. This is a different c1, by the way. This is actually ln of c1, but of this c1. But we won't worry about that right now. This can be simplified greatly to just be c1 times secant of x. So this integral then becomes the integral of c1 times secant of x times, and p was, guess what, tangent of x. Oh my goodness, I'm sorry. This is f of x. So this is actually f of x from earlier. Sorry, equals y times mu prime equals mu times f of x. If I had gone through the whole steps, then I would not have missed that. So you might start to see that this ends up just being some constant times the integral of secant squared of x with respect to x. And so what we end up having here is c1 times some constant, and we'll just say this is a second constant c3. Let c3 equal c1 times c2. So now the last step to do is to solve the differential equation. So y times mu, which is y times c1 times secant of x, equals c1 times tangent of x plus c3. And if we divide both sides by c1 times secant of x, we get y equals c1 and c1 cancel out in the first addend, I guess you would call this. Tangent of x divided by secant of x is tangent of x times cosine of x, which is sine of x. And c3 divided by c1 times secant of x is equal to c3 divided by c1 times cosine of x, which is just going to be another constant. And just for reasons of making this equation look nice, we're just going to say y equals x plus c times cosine of x. Now, somebody might ask you what's the largest interval over which this solution is solved, is valid. And so when we were dividing both sides by secant of x, as it turns out, you can't always just do that. So secant of x is, if you get a graphing calculator, you get a graphing. Okay, I'm not bad with technology. I don't know what's going on. Okay, here, mouse tool. If you get a graphing calculator, and I'm just gonna leave this whiteboard stuff up here. Don't mind it. You'll see that secant of x, we are worried about places where it is 0 or complex infinity. So it's never equal to 0, but at about negative pi over 2 and pi over 2, there are, well, discontinuities, where it jumps from something like very big number to very small number, very negative number, I mean. And those are the discontinuities. And that is it for this differential equation. Now, it also could be interesting to plot this differential equation numerically. So if we rewrite, the standard form is y prime plus tangent of x times y equals secant of x. Then if we rewrite this in terms of this form with the differential on the left side, we get y prime equals is 1 over cosine of x minus tangent of x times y. And we have here a little differential calculator, differential equation plotter I coded using a little bit of JavaScript ProcessingJS. I don't want to delete all that text, so I'm just going to move it out of the way. And if we just make it a little bit more computer readable, you see, wow, you are getting these nice lines. And to give you some sense of scale, each of these squares is side length 1. So if we want to zoom out a bit, we can see here. What function is this looking like? That's a good question. Let's see. This is a mysterious function, but you can see some stuff going on with this differential equation. Once again, each of these squares has side length 1, to give a sense of scale. And with that, we have solved our differential equation, found singular points, and plotted it. So thank you for watching. I hope this was helpful. By the way, I just remembered that my the Khan Academy website actually uses degrees for the trigonometric functions instead of radians. So it turns out when you multiply, when you convert the radians to degrees and then use them in the functions, you get a bit of a more interesting looking graph. So assuming these functions were then to instead take input of an angle in radians, it would look like this. And if you remove the unit squares, I'd say it's a pretty interesting graph. You can kind of see if the constant that we had from earlier was 0, then it's cos x times 0, and you just get the graph of sine of x. Like, here it is, the graph of sine of x. You can see at each of these points, and then you're adding a constant times cos of x. So we can also say, zoom out a bit, maybe 10 times. Maybe how about 3 times zoomed out. But anyways, all this differential equation graphing is starting to heat up my computer. Well, I hope this video was helpful to you. I certainly enjoyed making it, and see you next time.